Hello, I'm here today to show you the industry's first demonstration of a DDR4 controller and interface running at 2400 megabit per second with the industry's first 20 nanometer FPGA, the Xilinx Kintex UltraScale device. This demonstration showcases a 2400 megabit per second DDR4 memory interface operating with timing margin while transmitting a difficult data pattern. A robust memory controller and interface must do more than support I/O switching at fast data rates. Critical to the solution is the operating margin, which is required to ensure that voltage, process, and temperature variations are accounted for in your design. Here I have one of our memory verification and characterization boards featuring the Kintex UltraScale FPGA and a Micron DDR4 component interface rated at 2400 megabit per second. For this demo, I am going to walk through 4 steps. First, I will run a test that will write and read to the DDR4 memory to check the full functionality of the controller and interface. I'll be monitoring for errors with the LED on board. Second, I will look at the Vivado Logic Analyzer to observe the actual transactions being written and read. Third, I'll look at the margin of the DDR4 interface by overclocking the interface going from 2400 megabit per second to 2500 megabit per second. And lastly, I'll look at the Vivado Logic Analyzer to observe the results. Before I run the tests, let me first highlight a few things about the board and the setup. As you see here on the left side, the Kintex UltraScale board is powered by the general purpose power board, and the system clock is generated by the programmable clock generator. As you can see from the display, the input clock frequency is 450 megahertz. The FPGA onboard PLL generates a 1200 megahertz memory clock using the 8/3 multiplication ratio. Let's now go to the first step. This step is a test to check the functionality of the controller and interface. The test sends a series of write and read transactions to the 2400 DDR4 using the traffic generator logic included with our memory interface IP. In addition to the memory write and read commands, the memory interface design contains logic to compare the read data with the write data and generate an error when found. In this test, we use strenuous PRBS23 data patterns designed to emulate worst-case scenarios. The internal error signal is also connected to an external LED display on the board that counts continuously as long as there are no errors, and will stop if we have an error latched by the compare logic. The LED shows the transactions are running without errors. But for more in-depth look, let's take a look at the Vivado Logic Analyzer display. The write and read data pattern can be visualized with the Vivado Logic Analyzer running on my laptop with an in-circuit logic core inserted in the design. Here you see the Vivado Logic Analyzer display. I will highlight the Logic Analyzer console to verify the 2400 DDR4 interface is currently running error-free on the board. When we trigger with the instant trigger command, this will trigger the circuit logic core to send a snapshot of data being captured from the memory controller user interface over the JTAG cable to be displayed in the Vivado Logic Analyzer as you see here. An important signal to observe is the traffic generator compare error signal that is also driving the LED display. If we experience an error, the signal will change to high and the LED will stop counting. As you see here for the captured data, we do not see any errors. The read data and the write data are the same. You can also see here the read data valid signal turn high during read data periods. When we look at the data itself, you can see the PRBS23 pattern being used to stress the channel. Running difficult test patterns is key to ensuring a robust DDR4 interface. This capability of the Vivado Logic Analyzer can also be used for your own debugging purposes. Now on to step 3, the design's timing margin while operating at 2400 megabit per second. It's critical to have enough margin to handle varying voltage and temperature conditions with difficult data patterns. We are using a 2400 megabit per second DDR4. One way to check the design margin is to increase the input system clock frequency and in turn the memory clock frequency. We are going to overclock the interface to 2500 megabit per second to highlight the existing margin in the design. I can dial up the input clock generator from 450 megahertz to 470 megahertz while translating it into 1250 megahertz clock frequency or 2500 megabit per second data rate. It is above the specification of the 2400 DDR4 device, but is only running nominal voltage and temperature conditions. As you can see, the LED is counting, indicating no error. Let's now go to step number 4, Vivado Logic Analyzer verification of the overclocking. Since we have increased the frequency, let's now verify functionality with the instant capture capability and observe the captured data. As you notice, the error signal is not indicating any errors even at the increased 2500 megabit per second data rate. You have seen Kintex UltraScale FPGA DDR4 controller and interface running at and above the 2400 megabit per second data rate. Having this type of operating margin ensures that voltage, process, and temperature variations are accounted for in your design. Kintex UltraScale devices are shipping now. Use the latest release of the Vivado Design Suite and Memory Interface Generator to customize your memory interface and accelerate your design schedule. For more information, please visit xilinx.com/memory. Thank you for watching.